The Skoda Felicia is already recognized as being an excellent vehicle. It's stylish, roomy, well-built and reliable. Although the well-proven 1.3 litre pushrod engine provides adequate power for the Felicia, Skoda realized that some customers would like the option of a larger engine. With this in mind, Skoda have introduced a 1.6 litre engine. It's based on one of the Volkswagen Group's engines and is completely different in design to the 1.3. The 1.6 litre engine already meets the stringent 1996 European emission standards and features cast iron cylinder block with honed cylinder bores, 5-bearing crankshaft, aluminium cylinder head, toothed belt-driven overhead camshaft, hydraulic self-adjusting tappets, and multi-point fuel injection manufactured by Magneti Marelli. The Magneti Marelli engine management system has an adaptive learning program which enables the system to adjust to engine wear, different climatic conditions and driving styles. This means that routine adjustments of the CO content, idle speed and ignition timing are not required. Other than changing the spark plugs and air filter element, the system is maintenance-free. This video describes the main features of the engine and its management system and is designed to be viewed by the workshop technician. More detailed information can be found in the self-study program number 12. The book should be used in conjunction with the video to gain a more in-depth understanding of the subject. And remember, always refer to the workshop manual before carrying out checks, adjustments or repairs. The overhead camshaft, which directly operates the valves and drives the distributor, eliminates the previous rocker shaft and push rods. The engine therefore has fewer moving parts, and with only a crankshaft and camshaft, it's referred to as a two-shaft engine. The combustion chambers, which are of the Heron design, are incorporated into the pistons. This enables a much flatter cylinder head to be used and reduces the clearance between the head and the top of the pistons. The overall effect is to improve the mixing of the fuel-air mixture, resulting in more complete combustion. Combustion efficiency is further enhanced by the cylinder head's cross-flow design. To improve gas flow, the inlet air enters one side of the head and leave by the opposite side. The technically advanced inlet manifold is made of plastic. Therefore, to prevent damage, don't over-tighten the fixing bolts. Only tighten them to the correct torque. Engine lubrication is provided by a chain-driven oil pump, and the chain's tension is adjustable by moving the pump. Refer to the manual for the checking and adjustment details. The camshaft and water pump are driven by a long-life, quiet-running, maintenance-free toothed belt, the tension of which is maintained by a semi-automatic tensioning pulley. If you need to remove the belt at any time, then first make sure that the engine is set to the TDC position. If the belt is to be reused, then it must be refitted the same way round. Therefore, before removing it, always mark its direction of rotation. After removing the belt, to avoid the risk of the valve hitting the pistons, do not turn either the camshaft or crankshaft. If it is necessary to turn the camshaft with the belt removed, then first turn the crankshaft 1/4 of a revolution past or before the TDC position. To refit the toothed belt, first ensure the mark on the camshaft gear aligns with its reference mark on the casing. Next, check that the crankshaft is set to the TDC position by ensuring that the chamfered tooth aligns with its reference mark. Fit the tooth belt and tighten the adjuster's bolt by hand. Now turn the tensioner until the two marks are aligned. And tighten the nut to 20 Newton meters. The crankshaft must then be turned through 2 complete revolutions in the normal running direction, and the marks be checked again. The automatic tensioner's operation should now be tested by applying finger pressure to the belt. The tensioner should move back and forth if it's working correctly. Incidentally, after adjusting the belt, always check the ignition timing. The inlet and exhaust valves, which are directly driven by the camshaft, are fitted with hydraulic self-adjusting tappets. They use engine oil pressure to regulate the clearance between the valve and the camshaft. You'll find a detailed description of their operation in the self-study book, but here are a couple of important points to note. If the tappets are removed, then always store them the correct way up. This prevents oil escaping and airlocks developing, which can impair their operation. And to prevent possible engine damage after fitting new tappets, always allow 30 minutes to elapse before starting the engine. A point to remember is that the valves must never be reground. It's only permissible to lap them in with grinding paste. The engine's cooling system is of the closed-circuit type and therefore does not require routine inspection. However, for effective cooling, frost protection and corrosion prevention, it must be filled all year round with a mixture of 40% coolant and 60% water. The Bosch monomotronic system, as fitted to the 1.3 litre engine, uses a single injector and is thus known as a single-point injection system. In contrast, the new Magneti Marelli system has one injector per cylinder and is therefore known as a multi-point injection system, or MPI for short. The injectors are energized sequentially in the firing order, and thus the system provides a highly accurate delivery of fuel. The MPI system uses an electronic control unit to collect input information from a number of engine sensors. After analyzing the data, the control unit calculates and generates output signals, which in turn activate the fuel injectors and ignition system. The MPI system enables the engine to produce the ideal running conditions. For ease of explanation, we'll begin by looking at fuel delivery. Fuel is supplied from the tank by a submerged electric pump with integral non-return valve. From the tank, fuel flows via a filter and gallery to the injectors. Excess fuel is returned to the tank by the pressure regulator. The pressure regulator sustains a fuel pressure of approximately 3 bar, but it has another important function. It maintains a constant pressure differential between the inlet manifold air pressure and the fuel pressure in the injector gallery. Let's explain why. The quantity of fuel delivered by the injectors, spraying into the manifold behind each inlet valve, is determined by the length of time for which the injector is energized or opened. However, because on multi-point injection systems the injector nozzles are subjected to varying inlet manifold pressure, the quantity delivered would vary according to the changing air pressure. To overcome this, the regulator adjusts the fuel pressure by the same amount as the change in inlet manifold air pressure, and thus the fuel delivery remains constant. This is how the regulator works. Fuel from the gallery flows into the chamber and is partially restricted from returning to the tank by the diaphragm. The other side of the diaphragm is connected to the inlet manifold by a hose. The changing manifold pressure causes the diaphragm to flex, and thus the quantity of fuel returning to the tank is varied. In this way, the regulator constantly adjusts the fuel pressure in the injector gallery to compensate for the changes in inlet manifold air pressure. When the engine is switched off, the regulator closes the fuel return line. This enables a residual fuel pressure to be maintained between the regulator and the non-return valve in the fuel pump. The fuel tank ventilation system, which captures fumes from the tank breather and stores them in a charcoal filter, is controlled by the MPI control unit. With the engine running, the frequency valve is pulsed open at a certain rhythm, depending upon information received by the control unit. The valve's action allows the stored fuel vapors to enter the inlet manifold and supplement the fuel mixture, while fresh air enters the bottom of the filter to purge the charcoal. Now, let's look at how the rest of the MPI system operates. For the MPI control unit to calculate the exact fuel injection quantity and the ignition firing point, it requires input information from several sources. We'll look at them in turn. Firstly, there is the signal from the hall sender distributor. It supplies the control unit with engine speed information and a basic signal for calculating the ignition firing point. The distributor's interrupter plate has 4 gaps or windows. The window which corresponds with cylinder number 1 is wider than the others, and this allows the control unit to determine the TDC position of number 1 piston. The precise ignition firing point is calculated by the control unit after comparing input signals from several sources against a 3-dimensional map stored in its memory. To determine the best possible ignition firing point, an engine knock sensor is fitted. It detects the shock waves which occur in the engine when a cylinder starts to knock, or pink, and converts them into an electrical signal. The control unit determines which cylinder is knocking and automatically retards the ignition firing point in steps of 0.5 to 2 degrees up to a maximum of 15 degrees until the knocking is eliminated. If no further knocking occurs, the firing point reverts back to the normal setting as calculated by the ignition map. Inlet manifold pressure and air temperature signals are used by the control unit to calculate the injection quantity. Both values are measured by a combined sensor fitted directly into the manifold. The coolant temperature, which influences both the fuel injection quantity and the ignition firing point, is measured by an NTC-type sensor. The signal is also used by the control unit to determine the cold idling speed. The movement of the throttle butterfly indicates the driver's requirements, providing yet another item of important data for the ECU. The throttle's movement is recorded by a potentiometer incorporated within the throttle control device. A separate idle switch enables the control unit to recognize when the throttle is closed and the engine is idling. The signal is also used to activate the overrun fuel cutoff function. This switches off the fuel injectors to reduce exhaust emissions when the vehicle is decelerating. Exhaust oxygen content is measured by the lambda sensor. It's electrically heated to ensure that it reaches operating temperature quickly. The sensor's signal enables the MPI control unit to modify the injector's opening time, thereby ensuring that the air-fuel ratio remains as close as possible to lambda 1. This air-fuel mixture value is essential for the correct operation of the three-way catalytic converter. Having considered the control unit's incoming data, let's now look at its output signals. Firstly, there's the signal to the ignition transformer. The control unit calculates the ideal firing point, and at the correct moment it sends a signal to the transformer, which in turn generates the high-tension current required by the spark plugs. As we explained a little earlier, the fuel injection duration is calculated by the control unit after analyzing various input signals. Each injector is connected to earth via the control unit. So, by controlling the earth signals, the injector's opening duration can be altered to suit the fuel-air mixture requirements. Although the injectors are normally operated sequentially in the firing order, on first starting the engine, they're energized as a group. To protect the engine from mechanical damage due to over-revving, the injectors are switched off one by one between 5,600 and 6,000 RPM, and are switched off simultaneously if the speed exceeds 6,000 RPM. The fuel pump is supplied with voltage by a relay, which also supplies the heating element of the lambda probe. The relay is switched on by the MPI control unit only when the ignition is switched on and the control unit is receiving engine RPM signals from the distributor. Consequently, in the event of an accident, the fuel pump is automatically switched off as soon as the engine stops turning. Two further components receive their instructions from the MPI control unit: the charcoal filter's frequency valve and the electric motor of the throttle valve control device. The frequency valve's operating cycle depends upon coolant temperature, engine speed, engine load, and information from the lambda sensor. The throttle control device, which regulates the throttle butterfly in the nearly closed position, uses an electric motor, or actuator. The device performs these functions: idle speed regulation at all engine temperatures, throttle damping to ensure that the throttle closes slowly, and emergency running function, which enables the engine to idle in the event of an electrical failure. In addition to the throttle potentiometer and idle switch components we mentioned earlier, the throttle control device includes a second potentiometer to record the actuator's position. From this and other information signals, the control unit generates an output signal for the electric motor. In turn, the motor slightly opens or closes the butterfly to regulate the idle speed. In the event of an electrical failure, a tension spring opens the throttle sufficiently to enable a fixed but acceptable idle speed to be maintained. For smooth and precise control of the idle speed, the device has a specially shaped throat. Its design enables small changes in the idle air volume to be made for relatively large movements of the butterfly. The throttle control device is set at the factory, and no adjustments or repairs are possible. And please remember, due to this component's operation and the closed-loop fuel mixture control system, adjustments to either the idle speed or CO content are not possible. On vehicles fitted with an engine immobilizer, the MPI control unit performs another important function, that of communicating with the immobilizer control unit. The MPI unit generates a random code which is transmitted to and then stored in the immobilizer control unit's memory each time the engine is started. If, on starting the engine, the two codes do not match, then the MPI control unit switches the engine off after approximately 2 seconds. If you're unfamiliar with the immobilizer system, then please view video number 5. It explains the immobilizer's operation and how to approach fault finding. And here's one final point. The MPI control units of vehicles fitted with air conditioning receive additional signals from the operating switch and the compressor. The signals instruct the control unit to increase the idle speed slightly to compensate for the additional engine load created by the compressor. To improve performance, the compressor is also automatically switched off during full throttle operation. The Magneti Marelli MPI system has self-diagnosis. While the engine is running, the signals from the various sensors are constantly monitored. When the engine control unit detects an implausible signal, two things generally occur. A fault is registered in the memory, and a set value from the emergency running section of the control unit is substituted. In most cases, this allows the engine to keep running and the vehicle to continue its journey, although sometimes with reduced performance. To interrogate the system and identify the fault, you need the VAG 1552. Having connected it to the diagnosis socket and entered the address code 01 for engine electronics, these functions are available. 01, interrogate control unit version. 02, interrogate fault memory. 03, final control diagnosis. 04, basic setting. 05, erase fault memory. 06, end output. 07, code control unit. 08, read measuring block. And 10 for adaptation. Always begin testing by interrogating the fault memory to check if any faults have been detected. If faults are detected, then refer to the workshop manual. It lists the fault codes and likely remedies. Don't forget, though, that the cause of the fault may be due to defects with the wiring or connections, and not necessarily the component itself. You will need to test the circuits with a multimeter and refer to the current flow diagrams to locate the cause more precisely. The final control diagnosis function enables the throttle valve control device, frequency valve, and the fuel pump relay to be activated. You must look and listen carefully to confirm that the components are working correctly. Final control diagnosis can only be initiated when the ignition is switched on and the engine is stationary. Selecting function code 04 sets the MPI system into the basic setting mode. This function must always be entered after replacing the control unit, throttle control device, or after carrying out major engine repair work. The same function must be entered to check and adjust the basic setting of the distributor. With the engine at operating temperature and idling, enter function code 04 and display group number 01. An ignition timing figure of 6 degrees before TDC at 1300 RPM should be recorded. If the ignition timing is incorrect, then rotate the distributor until the correct figure is obtained. The idle speed returns to normal after exiting the test. Function 05, which erases the fault memory, and function 06, which ends the output, should already be familiar to you. However, you may not be quite so familiar with function 08, which calls up the measuring value block. After entering 08 and the appropriate display group number, it's possible to display groups of physical values from the MPI system. These include RPM, injector opening time, battery voltage, and air temperature, for example. Comparing the figures against those specified in the manual will enable you to monitor the MPI system's operation and identify components and/or systems which are functioning incorrectly. Unfortunately, there's insufficient time within this video to explain every detail of evaluating the measuring block values. All we would ask is that you spend a little time working on a vehicle together with the workshop manual until you feel confident. After all, practice makes perfect. Skoda has an enviable reputation for producing vehicles which offer exceptional value for money together with excellent after-sales service. The new 1.6 litre engine should further enhance this reputation as it provides more power, reduced exhaust emissions and increased flexibility. We therefore hope that you too will derive some satisfaction when working on this latest engine from Skoda.